Hello, this is Vatsal, and I'm going to present a paper on SemiMemes model. So let's start. This research provides a multimodal semi-supervised learning approach that outperforms other multimodal semi-supervised learning and supervised learning state-of-the-art models on two datasets: the Multimedia Automatic Misogyny Identification (MAMI) and Hateful Memes dataset. This method combines autoencoder and classification tasks to make use of the resourceful, unlabeled data. Let me give you some background. As memes have become more popular, there's a trend of creating memes that are not meant to be funny or amusing, but to express irony or to spread negative content on sensitive topics such as discrimination, race, gender, religion. Consequently, social media platforms are paying attention to the issue of meme sentiment analysis to prevent the dissemination of memes that contain harmful content. We can see here there are two examples where one meme is labeled hateful while the other is not, and this is based on image and text features. So how does this approach work? For our model, we develop a pre-trained model named cross-modality autoencoder, CHROME, which is based on clip features. The full form of clip is contrastive language image pre-training, and these features that can be trained on small datasets without labels. Next, we create a custom supervised model called Raw and Cook that incorporates the extracted features of both Chrome and Clip, hence utilizing knowledge from unlabeled data for a supervised model. Let's look at the methodology to understand it further. It consists of two steps. Step 1 is unsupervised pre-training. In unsupervised pre-training phase, we use the cross-modality or autoencoder and it is trained properly over there. Then in step 2, is supervised fine-tuning. A new model is designed for learning the classification tasks on label data. I'll go further into it using the architecture image. The initial step involves inputting a pair of image text into the clip model's image and text encoders to extract clip feature vectors, fimage and ftext. We can see clip model is used here, and these are the features of the clip, fimage and ftext. Chrome then uses one modality's clip feature to predict the other modality's clip feature. For example, we can say image feature fimage predicts text feature ftext at the end over here, and vice versa. This pre-training phase is carried out using only unlabeled data. Then a new model is designed for learning the classification tasks on labeled data. And first, the pre-trained encoders of Chrome are frozen to extract new representations from the original clip features, which can be seen over here. And then both the new representation and the original clip features are fused together to predict the classification target. So this is wait, where's my cursor? Yeah, this is the new feature which is made from the Chrome, and these are the original clip features. So they are fused together. The resulting model is called the Raw and Cook features classification model. Raw and Cook. What else? Yeah, here PRELU instead of the popular RELU activation function is used to ensure that the model learns the negative values of the encoder's output. We can see here that Chrome can be used to capture the underlying distribution of each modality for semi-supervised learning. Also, two Chrome models are trained separately using the mean square error loss function. Next, yeah, Raw and Cook model. Here we take only the encoder part, e-image, e-text of two pre-trained Chrome models and freeze them. That we already know. And the intuition is that Z-image and Z-text are informative features because they were learned on a large unlabeled dataset. Therefore, encoders are frozen to keep what Chrome learned on unlabeled data. However, both Z-image and Z-text were driven by different tasks. If we only use Z-image and Z-text for classification, it is not too powerful. Therefore, they decided to fuse Z-image and Z-text, thus Cook features, with the original features outputted from the clip fimage and ftext, raw features, thus the name Cook and Raw. Next, to prove the concept, and an experiment is conducted using MAMI and Hateful Memes dataset. Pre-processing and hyperparameter tuning is done to both SOTA and SemiMemes models. And we can see in the result, in table number 1, SemiMemes validation and test scores are higher than the other two models on 3 label settings. This performance gap decreases as the labeled samples increases. This demonstrates that with a large number of unlabeled examples, our method can be more advantageous than other SOTA methods. For hateful memes dataset, we can see in the table number 2, SemiMemes is also capable of achieving higher scores than Hate Clipper in all settings. The results of SemiMemes are not very higher than Hate Clipper on both development and test sets. However, when taking into account the number of parameters in each method, Chrome and Row and Cook included are significantly lower than that of Hate Clipper, with about 3.1 million parameters and compared to 1.5 billion parameters of Hate Clipper. Therefore, SemiMemes can save significant training resources while still assuring high performance. My only criticism with the research would be that even though this requires hours of research, they are not actually creating their own models. They just rearrange different methods which are available and thus optimize the performance. In my final project, I'm also working with sentiment analysis. Now, I'm not sure if I'll be using these models which are mentioned in this paper, as I'm working with text data and these models are developed for image data. Now, but one thing is I'm sure about is even though I'm not familiar with this topic, researching about different stuff from the paper like activation function, like PRELU, RELU, and other stuff definitely helped me understand sentiment analysis better. So I might not use the models from this paper, but I'll definitely use the methods which I learned over here. That's it from me. Thank you very much.